Hello, I'm Claire Butré, R&D Technical Leader at Quality Assistance, and I will present data obtained on the analysis of oligonucleotides by size-exclusion chromatography. Therapeutics oligonucleotides are short DNA or RNA chains of 15 to 35 nucleotides and have applications for a wide range of diseases. In general, mechanism of action of these oligonucleotides is to interfere during the translation of genes into proteins. Each nucleotide is itself built from 3 molecules linked by covalent bonds: a nitrogen base, a sugar, either a ribose for RNA or deoxyribose for DNA, and a phosphate or phosphorothioate group which acts as a linker. There are 4 existing bases which are presented here at the bottom of the slide. So there is adenine, cytosine, guanine, and thymine. And if we have an RNA molecule, the thymine is replaced with an uracil. In addition, we see a number of modifications on the oligonucleotide molecule. The phosphorothioate linkage, for instance, where an oxygen is replaced by a sulfur atom, and this modification prevents the molecule from degradation and enzymatic digestion. Modification on the sugar moiety by addition of methyl groups, for instance, leads to an increase in thermal stability. Furthermore, oligonucleotides can be single-stranded or double-stranded. The presence of multimeric species is one aspect of product quality, as it may lead to a loss in activity. In the case of siRNA, however, the presence of monomeric species would also be verified, as it might indicate a loss of activity. To separate the multimeric species from the monomeric ones, size-exclusion chromatography is the method of choice, as the separation is based on hydrodynamic size of the molecules, where large molecules cannot go through the different pores of the column and elute first. Smaller molecules penetrate the different pores and elute later in the chromatographic runs. Let's move on to the results of this study. We first developed a method using a size-exclusion column for separation of oligonucleotides coupled to a UV detector at 260 nanometers. For this study, a X-bridge column BEH 125 sec column from Waters was chosen. To define appropriate elution condition, we first tested the influence of ionic strengths on the chromatographic quality. For this, we tested 4 mobile phases with increased ionic strengths by increasing the NaCl concentration in a 0.2 molar phosphate buffer at pH 7.5. We also tested PBS as low ionic strength mobile phase. And the last mobile phase tested was one containing 0.05 molar phosphate buffer and 150 molar NaCl to have an overall concentration of 0.2 molar salts. And as we can see on the figure, increasing the ionic strength led to a delayed retention time, and peak shape was not improved. At high potassium phosphate concentration, we see a large peak, and increasing the salt concentration did not improve the overall peak shape. At a low concentration of phosphate buffer, the oligonucleotide elutes as a sharp peak, and based on this, it was decided to keep a low overall phosphate concentration in a mobile phase for the elution. The final condition chosen for sec separation with UV detection were PBS with this BEH 125 sec column. As discussed with the results before, the oligonucleotide nusinersen elutes as a sharp peak, and looking into more details, we see a peak in front of the main peak, which is most likely related to a dimeric state of the oligonucleotide, and there is also a shoulder on the peak indicating the presence of fragments in the samples. With these conditions, it is possible to obtain the relative quantification of each species, so the proportion of monomer, dimer, and fragments. This analysis can be performed as a routine test, as it is easy to set up. To identify the different peaks, other detection techniques are required. To gain more details on the samples, MALS detection can be used. MALS stands for multi-angle light scattering, and this detection leads to the measure of the absolute molar mass of the compounds, independently of the elution time. With MALS, the intensity of light scattered by the molecules is measured. This intensity is proportional to the weight average molar mass and to the concentration of components in solution. This is how the combination of mass detector and RI allows for mass determination of the component of interest. In addition, the data obtained gives information on the polydispersity and oligomeric state of the molecules. We have at Quality Assistance 2 MALS detectors coupled with HPLCs and RI detector for molar mass and size determination of molecules. To perform the SEC-MALS analysis, the conditions developed for SEC-UV were kept. Only here we used a larger column, so the same column type, but with a diameter of 7.8 millimeter and 30 centimeter length. And the same sample was injected, so the oligonucleotide nusinersen used as a model. We have here the same peak shape based on the UV signal as what was presented just before. And the additional information on this graph is the light scattering signal. And we expect for this sample a molecular weight of roughly 7,000 Dalton, and this is what we see here with the light scattering signal. For the peak eluting before the main peak, a molecular weight of around 14 kilodalton is calculated, which indicates the presence of dimer of the oligonucleotide of interest. With this detection, identification of the multimeric state of the oligonucleotide is possible, giving in-depth information on the sample. However, information on the fragment are not easily accessible on the MALS for such rather small molecule. To gain information on fragments, mass spectrometry is an additional tool that can be used. The mass spectrometry analysis was performed on a bioaccord system in a negative ionization mode, and we have used the same chromatographic column as in the detection UV setup, only we change here the mobile phase to have compatibility with the MS system, so we use 100 millimolar ammonium acetate. We see the elution of the peak both on the MS and on the UV on the graph on the left of the slide. And from the MS data, we have a spectrum. So this is the figure on the right, on the top right. And this spectrum can be deconvoluted. So this is the spectrum at the bottom of the right figure. And from this, we can identify the model oligonucleotide. So we see the molecular weight of 7,127 Dalton, which is the expected molecular weight for nusinersen. And we also see other deconvoluted peaks, which correspond to fragments of the oligonucleotide of interest, so missing 1 or 2 nucleotides. So they are annotated N-1, N-2 on this graph. Looking at the data in more details, by extracting the masses of the different compounds, we observe a trend in the elution of the fragment, which is as expected from the size-exclusion separation. We see increasing retention time for smaller fragments. In addition, from this figure, it is assumed that fragments which are N-4 or smaller could be chromatographically separated from the oligonucleotide of interest. So a fragment missing 4 nucleotides would be separated from the main oligonucleotide. And this means that this type of fragment, as it is separated from the main peak, could be quantified in routine analysis with UV detection. In conclusion, monomeric form of the oligonucleotide of interest can be separated from its fragment and from the high molecular weight species by size-exclusion chromatography. UV detection coupled to this separation can be used for routine analysis to determine sample purity. For more detailed information on the sample, the size exclusion can be coupled to a MALS detector or MS detection. MALS detection will give indication on the sample polydispersity and identification of the multimeric species. MS detection, on the other hand, besides exact molecular weight of the oligonucleotide of interest, gives information on the fragment and the molecular weight of the detected fragments. The work presented in this video is described in an application note that can be downloaded on the website of Quality Assistance. If you are interested in other separation techniques for oligonucleotides, please have a look at this other application note describing orthogonal method for characterization of oligonucleotides dealing with reverse phase, helic, and anion exchange separation. Thank you.